On February 25, 1991, an Iraqi Scud missile was moving toward Dhahran, Saudi Arabia. A Patriot battery was positioned to defend the air base, but no interceptor left its launcher. The incoming missile struck an army barracks and killed 28 American soldiers. The investigation found that the battery had been operating for more than 100 hours. During that time, a tiny error in the computer's clock had grown to 0.34-33 seconds. At the speed of the Scud, that was enough to shift the radar's predicted search window by approximately 687 meters. The system was looking for the target where it should have been, according to its own clock. The missile was already somewhere else. The Patriot did not process every radar return as a target. It used a range gate, a narrow predicted region where a tracked object should appear during the next radar scan. Returns inside the gate were examined. Returns outside it could be rejected as clutter or as the wrong object. To place that gate, the computer needed two things: the target's estimated velocity and the time since the previous detection. When both were accurate, the window followed the target. But a fast missile punishes even a small error in time. If the clock ran slightly behind, the gate also fell behind. After enough continuous operation, the Scud could pass through the radar beam while remaining outside the piece of the beam the tracking algorithm was willing to process. Inside the system, elapsed time was counted in tenths of a second as an integer. To use that value in targeting calculations, the software converted it into a real number stored in a 24-bit register. The conversion could not preserve the full precision of 1/10. Each calculation lost only a tiny fraction of a second. For a system running a few hours, the loss appeared small, but the error was tied to total uptime. It did not reset between targets. At 1 hour, the calculated time was short by 0.0034 seconds. After 8 hours, the gap was 0.0275. The software was not suddenly wrong. It was becoming steadily less right, one conversion at a time. The Patriot had originally been designed as a mobile air defense system. It was expected to move and restart, not remain in one fixed position for days. In the deployment at Dhahran, that assumption changed, but the timing logic did not. Israeli operators supplied data showing a 20% shift in the range gate after only 8 hours. Army officials said a 50% shift would prevent the system from tracking a Scud. Extrapolating the data placed that point at about 20 hours of continuous operation. A reboot every few hours would reset the clock, and it took roughly 60 to 90 seconds. But Alpha batteries stayed online for more than 100 consecutive hours. By then, the GAO estimated the gate had shifted 687 meters from the target's center. The problem was not completely invisible. Engineers analyzed the Israeli data and produced software that compensated for the inaccurate time calculation. The modified version was released on February 16th. 5 days later, the project office sent Patriot users a warning. Very long run times could shift the range gate and offset the target, but the message never defined very long. It did not say 20 hours. It did not impose a reboot interval. Officials assumed other batteries would not remain online long enough to fail. On February 25th, that assumption met Alpha battery's real operating schedule. The system did not track the incoming Scud and did not engage. The corrected software reached Dhahran the following day. A fix existed. A warning existed. Neither became protection in time. This story is often reduced to a rounding error, but the rounding error was only the first link. A mobile use assumption became a continuous use reality. Endurance testing did not cover the new operating pattern. The system had no embedded performance recorder. A known workaround was not translated into a quantified limit. A software correction moved through a wartime distribution chain too slowly. Each layer expected the others to keep the risk small. Reliable systems treat uptime as an input, not background. They test beyond intended duration, monitor numerical drift, force safe resets, record internal state, and write warnings with numbers and actions. 0.34 seconds did not suddenly break the Patriot. The system had been accumulating failure for 100 hours. This is fault cascade, where small errors outlive the assumptions designed to contain them.